Welcome to Cambridge IGCSE Physics, Lesson 55.1, What is radioactive decay? Today we explore the fundamental process by which unstable atomic nuclei change and emit radiation. This is core content for your examination and forms the foundation for understanding nuclear physics. Let's examine our learning objectives for today. By the end of this lesson, you will be able to first know that radioactive decay is a change in an unstable nucleus. This means understanding that certain atomic nuclei are not stable and must change to become more stable. Second, know that nuclei may emit alpha, beta, or gamma radiation during decay. These are the three main types of radiation produced. Third, know that these changes are spontaneous and random. This means they happen naturally without external influence, and we cannot predict exactly when any individual nucleus will decay. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, radioactive decay, which means the process where an unstable nucleus changes its structure to become more stable. Second, unstable nucleus, which means a nucleus containing excess energy that requires change to reach a stable state. Third, emission, which means the release of particles or energy from the nucleus during decay. Fourth, spontaneous, which means occurring naturally without any external cause or trigger. Understanding these terms precisely is crucial for mastering nuclear physics concepts. Let's explore our first core concept. What is radioactive decay? The fundamental principle states that unstable nuclei change to become stable. This is a universal law of nature. Everything tends toward its most stable state. The definition is, radioactive decay is the spontaneous change of an unstable atomic nucleus, resulting in emission of radiation. Let me explain each part. Spontaneous means it happens naturally, unstable nucleus means the original atom's center has excess energy, and emission means particles or energy are released. The key features are, first, the original nucleus transforms into a different nucleus with different properties. Second, energy is released as radiation particles that we can detect. Third, the process continues until a stable nucleus is finally formed. The diagram illustrates this transformation from unstable red nucleus to stable green nucleus, with orange arrows showing radiation emission. Now we examine the types of radiation emitted during decay. There are three main types: alpha, beta, and gamma radiation. First, alpha radiation, written with the Greek letter alpha. This consists of a helium nucleus containing exactly 2 protons plus 2 neutrons. It's relatively heavy and moves slowly. Second, beta radiation, written with the Greek letter beta. This is a high-energy electron that originates from within the nucleus itself. It's much lighter than alpha and moves very fast. Third, gamma radiation, written with the Greek letter gamma. This is an electromagnetic wave carrying pure energy with no mass or charge. Each type has different properties, including different penetrating power and ionizing ability. The diagram shows all three types emerging from a central nucleus N, with alpha shown as the thickest red arrow representing heavy particles, beta as medium blue arrow for lighter particles, and gamma as thin green arrow for energy waves. Let's work through our first example. The problem states, a radioactive sample contains 1,000 unstable nuclei. After 1 hour, 250 nuclei remain unchanged. Describe what happened to the other nuclei. We are given initial nuclei equals 1,000, remaining nuclei equals 250, and time equals 1 hour. We need to find an explanation of what happened to the missing nuclei. Step 1. Calculate decayed nuclei. We subtract 1,000 minus 250 equals 750 nuclei. Step 2. These 750 nuclei underwent radioactive decay. Step 3. Each nucleus became a different, more stable nucleus with different properties. Step 4. Each nucleus emitted radiation, either alpha, beta, or gamma during the decay process. The answer is 750 nuclei decayed spontaneously, transforming into stable nuclei and emitting radiation in the process. Example 2 explores why radioactive decay is random. The problem asks us to explain the random nature of radioactive decay. Let's analyze this systematically. First, we cannot predict when any individual nucleus will decay. Even identical nuclei in identical conditions decay at different, unpredictable times. Second, each nucleus has an equal probability of decaying in any given time period, regardless of its age. Third, although individual decays are random, large samples show predictable patterns that we can measure and use. Fourth, the process is completely natural with no external triggers determining when decay occurs. The conclusion is that randomness applies to individual nuclei, not to large populations. The graph shows this principle. While we cannot predict individual events, the overall pattern follows a predictable curve called exponential decay. Let's examine the spontaneous nature of radioactive decay. The key characteristic is that radioactive decay happens naturally without any external influence whatsoever. Understanding what spontaneous means is crucial. First, no external energy input is required. The nucleus contains enough internal energy to drive the process. Second, the process cannot be started or stopped artificially. We cannot turn radioactive decay on or off like a switch. Third, decay occurs at a constant rate for each specific isotope. This rate is called the half-life and is characteristic of each radioactive element. Fourth, the process is independent of temperature, pressure, or chemical state. Environmental conditions do not affect nuclear decay rates. The practical implications are significant. First, radioactive materials always emit radiation continuously. Second, the rate depends only on the number of unstable nuclei present. Third, the process continues relentlessly until all nuclei become stable. Now practice what you've learned with these three questions. Question 1 is basic level. It asks, state 3 types of radiation emitted during radioactive decay. This tests your knowledge of alpha, beta, and gamma radiation. Question 2 is intermediate level. It states, explain why we cannot predict when a specific nucleus will decay. This requires you to apply the concept of randomness we discussed. Question 3 is advanced level. The question is, a sample has 800 unstable nuclei. After 2 hours, 200 remain. Calculate how many decayed and explain the process. This tests your analytical skills and understanding of the decay process. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how radioactive decay applies in practice. In medicine, radiotherapy uses controlled radiation from radioactive decay to treat cancer by targeting tumor cells while minimizing damage to healthy tissue. In energy production, nuclear power plants harness the enormous energy released during radioactive decay to generate electricity for millions of homes. In archaeology and geology, carbon-14 decay provides a natural clock that determines the age of ancient objects and fossils. In safety technology, smoke detectors use alpha radiation from radioactive decay to detect smoke particles and warn of fires. These applications show why understanding nuclear physics matters. Career-wise, this knowledge leads to many professions. Nuclear physics advances our understanding of matter, medical physics applies radiation safely in healthcare, power engineering designs safe nuclear facilities, and research develops new applications. The concepts you learn today become tomorrow's life-saving technologies. Let's review the solutions. For question 1, the answer is alpha, beta, and gamma radiation. These are the 3 main types emitted during radioactive decay, each with different properties and penetrating power. For question 2, we explain that decay is random because each nucleus has an equal probability of decaying, but the exact timing is unpredictable for individual nuclei. We can only predict statistical behavior of large groups. For question 3, we calculate 800 minus 200 equals 600 nuclei decayed. Each of these nuclei transformed into a more stable nucleus and emitted radiation during the process. Now, exam success tips. First, always show you're working. Even if the final answer is wrong, you earn marks for correct method and approach. Second, include units in all numerical answers. This is essential in physics. Third, use key terms correctly. Spontaneous means natural, random means unpredictable timing, unstable means excess energy, emission means release of particles. Fourth, read questions carefully. Describe means state features, explain means give reasons why. Let's summarize today's lesson on radioactive decay. The key points to remember are, first, the definition. Radioactive decay is the spontaneous change of an unstable nucleus into a more stable form. This is the fundamental process driving all nuclear transformations. Second, radiation types. 3 main types are emitted during decay: alpha particles, which are helium nuclei, beta particles, which are high-energy electrons, and gamma rays, which are electromagnetic waves. Third, the nature of the process. Decay is spontaneous, meaning it occurs naturally, random, meaning we cannot predict individual events, and continuous, meaning it never stops until stability is reached. Fourth, the result. An unstable nucleus becomes stable and energy is released as radiation. For further study, review the properties of different radiation types and their penetrating power. Practice decay calculations and half-life problems to build confidence. The next lesson covers nuclear equations and transformations, which builds on today's work by showing how we write and balance nuclear reactions. Ensure you understand today's concepts before moving forward.